Dear students, just a moment. Dear students, welcome to my course on metamorphic phase equilibrium. And this is my first lecture. This week, I told you you have 3 classes. So I will be taking technically 3 lectures. And I will upload them, and as I have told you, you will be able to access it. But this week I will take 2 lectures because I gave you a lot to study in the 2 periods. And I request you to spend a lot of time looking at the derivations. The significance of all that I will teach you, but the point is I would like to know that you have read this week and in the next week a considerable amount of thermodynamics. At the moment you will be reading without context, just as an exercise. But as we progressively move down more video lectures, you will find that they have great relevance. And metamorphic phase equilibria cannot be taught without thermodynamics. It is not possible. So, chemical thermodynamics is our foundation. And we will take parts, we will take derivations, part derivations from what I have given to you, and we will apply it on the board. It's not possible for me to take a full chemical thermodynamics course. It's just beyond the time scales. So I have asked you to read it, and I have given you a video lecture so that you can spend your time. You can do it at your own time and you study. Otherwise, for the classes, and some of you have raised questions about that. You might have some questions. Normally, students do understand all, and they understand it well. And if you have questions, we'll figure out a way that I answer your questions. But for the moment, I think we start the course, Metamorphic Phase Equilibria. We will merge chemical thermodynamics and metamorphic fluid equilibria at some point of time, and you will see it's just blended into it. So right now, I will start with metamorphic phase equilibria. Now, metamorphism is a process. It is a process by which a rock experiences mineralogical and chemical changes in response to changes in pressure, temperature, conditions that act on it. Now that is important. Rocks left to themselves would never do anything different. It will just stay there with whatever it is without any changes. A rock once formed at a particular set of conditions will not change unless the external conditions to the rock changes. So we have in a rock what is called a system, and you have something called a surrounding. These are the 2 things of chemical thermodynamics which is relevant to us. System and surrounding. Our rock is our system. When I say a rock, now it's a big word. Say for example you take a niece or nice or whatever you say, or take a niece of dark colored layer and leucocratic layers. And you can crush the rock and make a powder of it and then analyze it. That's the composition of the rock. But you must understand, the rock was mineralogically heterogeneous. Mineralogically heterogeneous between the leucocratic bands and the melanocratic bands. But what you did is break it into small pieces, put it in a crusher, make it powder, and take the powder and analyze it, you get a composition of the rock. That's the composition of the rock, not of the layers. So then your rock, that rock powder is your system, is your chemical system. But somebody working on certain other aspects might say that, okay, I would like to differentiate the rock into two parts. I would like to work on the dark bands and the white bands separately. So what I could do is slice the dark bands and slice the white bands and analyze it separately. Crush it, grind it, but separately. And once you do that, then you have a light colored band and a dark colored band. And the light color band represents the composition of the particular system, if you want to choose, and the dark colored band is another composition that you want to choose. But whatever it is, whenever you take each of the crushed powders, you're looking at a particular chemical system. It's also a mineralogical system, but it's essentially first a chemical system. It can so happen that, say, in the dark band, you have a mineral A and a mineral B, a mineral A and a mineral B, and a mineral C is formed through a reaction between A plus B is equal to C, and this is C. But where, for example, this is also B, and this is also A, and this is also A, then if you take the whole system, you're possibly making a mistake. Then you have to go to what is called subsystems. So you can take a rock, you can take the different layers. Within an individual layer, you can see this mineral C forms at the interface between A and B. So it's an interface control reaction. So if you have an interface control reaction, then that has a particular system. Okay? That has a particular system. So you can take it as that part of a system. Or, say for example, your mineral A has two crystallographic sites, say M1 and M2 site. I don't know whether you know it. Say for example, if you take a mineral called Mg2Si2O6. Now, this formula is astatite. Or you can have its iron counterpart, which is called ferrosilite. So Fe2Si2O6 and Mg2Si2O6. Mg2Si2O6 is one end member of the phase, and Fe2Si2O6 is another end member, and the phase is Mg, Fe whole twice Si2O6, and this mineral is called orthorhombic pyroxene, or you might have heard the name as orthopyroxene. So this orthopyroxene, which is a mineral phase, has two components, enstatite and ferrosilite. Okay? But this, when I talk about it, this silicon, for example, is on a tetrahedral site, and this is on an octahedral site. Magnesium and iron are competing for a position on the crystallographic octahedral site, whereas silicon is in the tetrahedral site. And there are two octahedral sites in the pyroxene. You see? This is called, one is called M1, the other one is called M2. Both are octahedral. You see, both of them here, the two sides are not differentiated. But they are energetically different sides. And so, you can have magnesium and iron in one octahedral site, which is called the M1 site, which is small in size, and you have a larger MgFe site, which is essentially a larger site. So if you take the two sides, they are non-equivalent and they have different energy levels. So what happens when you take magnesium and iron and when they have to decide in this orthoperoxide as to where they are going, then that requires an understanding of how magnesium and iron partitions between the two octahedral sites in orthopyroxene, namely M1 and M2. So, we had the rock itself with the bands, we had the different bands, and then we had interface control reaction subdomains, and here what we are talking of, it's even a smaller scale, where even a mineral grain now is dissected into crystallographic sites which are occurring in the scales of angstrom to micron scale, angstrom to micron scale. So your system here is now angstrom to micron scale. Here it's in the micron scale. If you take a gneissic rocks and take the different layers, those are in a couple of centimeter scale. And when you take the rock, these are in meter scale. So the scale of the system will change depending upon what you want. It's your problem. How will you define the system? How will you define what is the scale of the system? What is the composition of the system is essentially your problem. But once you decide it, the rest of it is the surrounding. There is no distinguishing the surroundings. The surrounding is a homogeneous matter. There is no further subdivisions of the surrounding. Once you choose a particular system having a particular scale. Now that is very important. So when you're talking about metamorphism of a rock, the first thing that should come out, what is my problem? What am I looking at? What do I want to find out? Those are the questions that you first ask yourself. And once you have an answer, then you look as to which of the system, angstrom to micron, few tens of microns, centimeters, couple of centimeter scale layers, or the rock itself. Which scale you will be talking about. Now this is essentially dependent on the user. But once you have a particular system of your choice, which you want to deal with it, everything else is surrounding. Now, every rock, whether it's a sedimentary rock, a metamorphic rock, they form at a particular pressure temperature condition, or an igneous rock, they form at a particular pressure temperature condition. If you don't change any of these pressure temperature conditions of the rock, if you don't change it, then the rock by itself doesn't do anything. It won't change. It won't change. It just doesn't change. It doesn't respond. Because the surrounding, which the changes are brought about the surrounding. So the surrounding maintains the status quo of the pressure temperature conditions. Then the system stays put. Nothing happens. But, say for example, if you go to Greenland, for example, where it's completely snow-covered for most of the year, and when it's summer, a bit of the ice melts and the rocks are exposed, and you see very fresh rocks. But if you go to India, for example, and do field work, you don't get so-called clean rocks. Much of it is weathered. Sometimes we have to break open the upper scum and bring in the fresh rock from inside. So you can say, sir, if the rock is there on the surface, it's changing, obviously it's changing, it's undergoing certain reactions. Yes, because the rock that you see on the surface of the earth, and you pick it up, didn't form there. They didn't form there. They formed, especially metamorphic and igneous rock, they formed somewhere deeper. So once you brought it from deep to the surface, you changed the surroundings. And the rock was merely responding to the change in the surrounding conditions. So remember, a rock has a long history, a long memory. It doesn't change its mineralogy or chemistry unless acted upon. And when it is acted upon by the surroundings, then it responds to the changes. It merely responds to the changes. That is why metamorphism is a process by which a rock changes its mineralogically and chemically in response to changes in pressure, temperature, and conditions. Now, those pressure, temperature conditions are not inbuilt in the rock. That's in the surroundings. Now, that's the first thing that you should understand. It's the surroundings that change, that force the rock to respond. Because the rock is no more formed at a particular pressure, temperature. And if the pressure, temperature of the surrounding, or the fluid condition of the surrounding is changed, then the rock is not in equilibrium with it. And the rock always tries to attain equilibrium as you change the surrounding conditions. And then, while this happens, there are three ways in which system and surrounding interact. You know this. One is called closed system. Sorry, not closed system. I'm sorry. Isolated system. In this case, the system and the surrounding does not exchange energy, does not exchange mass with the surrounding. So the system and the surrounding does not exchange either energy across the interface or mass across the interface. So a classic example is IIT Kharagpur, for example. The whole world collapses, IIT Kharagpur just stays put. No response, blacked out. So that's it. That's an isolated system. No interaction with the surroundings. That's why you're at home and I'm teaching from here. Right? That's a classic example of isolated system. They have no communication across the interface. Neither they exchange energy nor they exchange mass. Then the second is what is called a closed system. Remember, our system is the rock. In this case, the two exchange energy, but not mass. No mass is exchanged across the interface. These are called closed systems. These are called closed systems. That means, in this case, if the temperature or the pressure of the surrounding changes, the system will respond in a way that it equilibrates with the changed condition of the surrounding. The system will respond to this change in the surrounding by doing a few things by itself. But if you don't change the pressure temperature conditions, the rock does not respond. Just not. And then you have what is called the open system. In this case, the rock system and the surrounding, the rock and the surrounding exchanges both energy and mass across the interface. What is then the difference between this closed system, no exchange of matter, mass, this system, exchange of mass? And this can occur over various scale. We don't go into that anymore. I will come to that at the end of the lecture. So what happens here? In an open system, the composition of the rock, the composition of the system changes. In this case, the composition of the system does not change, or the rock does not change. Here, no interaction between the system and the surrounding. So there are three ways in which the rocks interact. This is an absolutely theoretical thing that is irrelevant to a metamorphic pathologist. This never happens. It has never been proved, it has never been shown, it has never been described. So if you happen to be one, then you really get the kudos for it. But it is obvious that such things don't happen in metamorphism or in natural processes. Closed system is the one which people normally work with. Closed system. That means the composition of the rock of the system does not change. But this is, over the years, people have worked taking closed system. Because why? If mass does not change, then you have taken care of a lot of variables. Lot of variables don't change. But if mass changes, and you don't know how the mass changed with time, then it's very difficult to model it. And in open system, there's a continuous interaction of mass between the surrounding and the system. So there is matter going in and going out. It could also be not all the elements are going in or going out. Some elements are not interacting. Some elements are interacting, and it becomes a very, very complex system. This open system is given another name called metasomatism. It is a type of metasomatism, because you can see what happens when you have to change mass. You need some material, some waves have to migrate across system surrounding interfaces. Have to migrate across system surrounding interfaces. There are two mechanisms to do it. Only two, or a combination of them. Two end members or a combination of them. What is it? One is called molecular diffusion. What is it? That a particular mineral or a particular part of the system and a particular part of the system and the surrounding, there is a difference in the composition of the two. Have you understood? There are two parts in the system of a particular mineral, and there is a difference in composition. So what happens with molecular diffusion, when there is a chemical gradient, there is attempts to do what is called molecular diffusion. From elements jump from one space, one vacancy to another vacancy to another vacancy, and similarly others follow the path. So that is what is called molecular diffusion. And the other diffusion, which is easy to conceive, that is what is called advection. A-D-V-E-C-T-I-O-N, advection. What is advection? Advection is, in contrast to molecular diffusion, which occurs because of a chemical gradient, advection normally involves a fluid. Advection normally involves a fluid, where when the fluid migrates, for a fluid to migrate, there has to be a hydraulic gradient. So if there is a hydraulic gradient, fluids will migrate. And so once fluid migrate, the dissolved species and bring out species, controlled by the compositional variations. So you have to do this compositional changes, you have to do at the end of it either a molecular diffusion or a advection. Now, molecular diffusion may be a strong process at high temperatures, at very high temperatures, because you know at low temperatures molecular diffusion is strongly impeded. It's strongly impeded. But at high temperature molecular diffusion rate is faster. But advection can occur at any temperature, and it depends on pathways of migrating fluids. The pathways along which fluids migrate. How are these pathways generated? These pathways are normally induced by deformation of the rock. Because when you deform, the rocks develop weaknesses along which fluid starts to migrate and interact, dissolve, take out, and generate parts. So these are the two ways in which mass is exchanged between the surrounding and the system, by molecular diffusion or advection. Either case. But these are the two end-member process. High temperatures, you can have both processes operating together in tandem. At low temperature, normally for metamorphic rocks, molecular diffusion below 550, 600 degrees centigrade is very difficult. So what happens? At very low temperature, molecular diffusion is, as a process, it's a subsidiary process. And most mass transfers occur along only the fluids. So we have now talked a little bit about the rock, which is a part of our system, the scale of which can change depending upon what you want to do with it, and then the rest of the surrounding. And there are three ways in which the system surrounding interacts. Isolated system, no exchange of energy and mass. Closed system, exchange of energy, no mass. And open system, exchange of energy and mass. How is mass exchanged? Either through molecular diffusion or through advection or both coupled together. Now, actually what happens in the laboratory class which is associated with this, there are many textures that can be shown, where these things, you can show it right under your eyes on the microscope. And you can also find out how, with respect to a multiply deformed rock, when it happened. I don't know how to do this online class. I will try my level best, but I know I will fail. Because I don't think microscopy can be done by other methods. Identifying a mineral is not metamorphic petrology. Metamorphic petrology starts after that. But we will talk about that later on. But for the moment, I guess you get this system surrounding interfaces. Now we come to a little different point. I have been telling you a little bit that the surrounding, if it changes its pressure, temperature, condition, the system responds. Why it responds? Because the rock was formed at a particular pressure, temperature condition, fluid condition. But if you change those conditions acting on the rock, then the rock is out of tune with its surroundings. So what happens in closed and open systems where energy can be exchanged, the rock can feel the heat. Have you understood? Can feel the change, and it tries to re-equilibrate to the new pressure temperature conditions. Re-equilibrate to the new pressure temperature conditions. And that's what it tries to do. And metamorphic petrology is based on one single thing. What does the rock do? Now, there is a particular term some of you may know this. I think you know this expression. G is equal to G0 plus RT ln activity. Many of you have studied this in school. G is equal to G0 plus RT ln A. Now, if I write this on this is written, but it is not complete. Thermodynamically, it's a third-class sentence. But you've read it this way, because not much was given to it. If I write it in the correct way, this is a better way. What it does is, now here, let me start to get into a little bit of chemical thermodynamics. This term is called Gibbs free energy. This is called Gibbs free energy after the great person called Willard Gibbs, who wrote these equations about 130 years ago. G is called the Gibbs free energy. Why free energy? I am not, a little bit is written in the PDF, but I can't go into the details of it. The only thing that is, in the rock you have what is called internal energy, which can be divided into mechanical and non-mechanical energies. This free energy, this G, is called the Gibbs energy and is free from any mechanical requirement that is necessary for the internal energy of the rock. So G is called the free energy, free from the mechanical aspect, available for chemical reactions. So this is called a Gibbs free energy. This is also the same except for this nice superscript G0. We'll talk about it a little later. Then you have R, and this is R is called the universal gas constant. Now just before going to R, G, the chemical free energy, it may have a unit calories or joules. Do you understand? Calories or joules. Previously, when I was a student like you, we used to use calories. But nowadays, things have changed. It's conventionally joules. But it doesn't matter. They are convertible. Okay? So, joules can be converted by multiplying a number, and you can get the number into calories, or calories into joules. Now, so this is, if this is, say, for example, let's say we take it calories. If this is in calories, then this is also in calories. Has to be, because G is equal to G0. There is nothing after that. So, for units, G0 also has the unit of calorie. Now, R into T. You remember from your school days, activity has a dimensionless number. That means it doesn't have an unit. Activity does not have an unit. So this has no units. It's a mathematical dimensionless operator. So you have R into T. So what should be the unit of R? You see, the unit of R should be, this total has to be calories, because this is calorie, this is calorie. This total has to be calories. So if this has to be calories, then, and it is multiplied by temperature, so R should be calories per degree Kelvin. You know, in thermodynamics we use kelvins. So calories per degree Kelvin. So universal gas constant can be written as calories per degree Kelvin, and then what is called mole. This one, G here, is calories per mole. Do you understand? G is in calories per mole, G0 is calories per mole, and R is equal to the universal gas constant is calories per Kelvin per mole, you know, in here, this Kelvin is multiplied by this Kelvin and they cross off and you get calories per mole. So essentially, you get calories. So this value is 1.98717. This is the unit of R in calories per Kelvin per mole. And in joules it is 8.3143 joules per Kelvin per mole. If you divide this by this, you will get a value which is close to 4.184. Joules is 8.3143. If this value is 1.98717 calories and the same value is in joules is 8.3143. If you divide this by this, you will get a value of 4.184. That means if you take joules and divide it by 4.184, then you get calories. Have you understood? Or 1 by 4.184, 1 by 4.184 is equal to 0.3. You find out the number. I think it's 3 to 9. I don't have the calculator here, so you can put it right in the calculator. So 1 by 4.14 is just the opposite. I think it's 0.239. Please check it out, yes, the calories. So nowadays, because I've forgotten the conversion factor, but it's 8.3143 joules and 1.98717. So if you take the joules and divide it by 4.184, you get calories. Right? So these are the units of this fundamental equation. Chemical free energy is equal to G is equal to G0 plus RT/LNA. This one here is the same, except that I have written pressure temperature here and pressure temperature here, meaning that this free energy equation here, equation of state, it's called, this equation of state is at a particular pressure temperature condition. If you happen to change the pressure temperature condition, we will have the same equation, but the numbers would change because of certain conditions. Okay. Now, I have written this. I will just give you one small hint. I was talking about what is the difference between this G and this G0. When I ask in the class, normally physical classes that we have, the first thing that people say is, at standard state. Wrong. Completely wrong. It's not standard state. But before I explain it more, let me give you a clue. For a pure phase, activity equal to 1, I think you know this. Activity is equal to 1. So if activity is equal to 1 for a pure phase, and if I put instead of 1A, I put 1, then this term becomes 0. Have you understood? So RT/LNA becomes 0. So if RT/LNK becomes 0, then GPT is equal to G0PT. What is happening? Can you tell me? What is happening? When I make this activity equal to 1, that is of a pure phase, then this term becomes 0. And therefore, this term becomes equal to this term. Or in other words, if I tell you, what is the difference between G and G0? So G, pressure temperature, is the free energy of a phase component. I will tell you this. What is this? I will now write about phase components. Talk to you about phase components. Free energy of a phase component at equilibrium PT. This is what is G. And you can ask me, and what the hell is G0? Wait a minute. G0, pressure temperature, is the free energy of a phase component, of a phase. If it was pure, at equilibrium PT. Did you get this? Mark the words. Free energy of a phase component at equilibrium pressure temperature, and G0 PT is the free energy of a phase if it was pure at equilibrium pressure temperature. That means if I go to this expression, this is the free energy if pure. And what is this? What is this? If activity is equal to 1, as in a pure phase, RTLN is equal to 0. But if the phase is impure, then you know from your class 11, 12 that activity is less than 1. That means it's a decimal. Yes or no? So if it's a decimal, then ln of that will be negative. Universal gas constant is positive. Temperature in kelvins is always positive. Multiplied into negative. So this value, whatever that value is, can be written as free energy of impurity. Because A less than 1 means there is impurity. Multiplied, ln of that is negative. And the whole word becomes negative. So this is the free energy of impurity. And this is the free energy of purity. And G is the sum total of it. Or G is the sum total of it. For a pure phase, this term vanishes. And you have G is equal to G0 PT. Okay, all of you, are you with me? Right. So, in this expression, we have two components. Free energy of purity, free energy of impurity. At equilibrium pressure temperature condition. Algebraic sum of this is the free energy, which is GPT. G0 is not standard state. It's wrong. Then you have to define your pressure temperature as standard state. But this is actually what it is. Now, so we come to the first part, a good conclusion. And then you can write this in another way. And I leave this for you. I can write also RT ln A is equal to right? Of course, G is the total free energy. G0 PT is the free energy if it were the pure phase. And if you take the subtraction, that's the free energy of impurity. Isn't it? That's what you said. Free energy of impurity. So that is how it is. So RT ln A is equal to GPT minus G0 PT. Now I come to a point which we will put in later, but for the moment, before we finish this video lecture, I would just like to introduce an important point here. phase and phase component. Some of you may know, some of you may do not know, and those of you know and those of you do not know, you can listen to me once again, because it will clarify misconceptions. Now, if you take a system which is your rock, you have different minerals. I take two, let's say we take two. Let's say there are two minerals, A and B. This is A and this is B. If you go to a microscope and you look at the rock, you can physically see it. If you know the minerals, if you know the property of the minerals, you can identify the minerals. That means a system is composed of different minerals. A rock has composed of different minerals. Each of these minerals have certain distinctive properties by which you identify them. Also, they have distinctive compositions. Say, for example, quartz, SiO2 100 weight percent. But if you take Al2 SiO5, then Si is roughly around 33%. Aluminium is 67%. So what happens is that in a system there could be single mineral or multimineralic. So one single mineral, a monomineralic rock, or multimineralic rock. It doesn't matter. But there are different minerals with distinctive properties, well-defined boundaries, and whose composition vary within known limits. This is what is called a phase. This thermodynamically is called a phase. So, for example, you have quartz, for example, is a thermodynamic phase in a rock. And say, for example, you have, say, orthopyroxene. We talked about orthopyroxene, so it's a very odd assemblage anyway. It doesn't matter. Another mineral is, say, this is A and this is B. Quartz and orthopyroxene. Quartz and orthopyroxene. Now, orthopyroxene is a very complex mineral. You may not know it, but we will see the metamorphic petrology. It's a very complex mineral. It's not so simple. It appears to be simple. It's not simple. It's very complicated. But let's make it simple. So, like quartz, for example, is SiO2. Orthopyroxene has the formula MgFe whole twice Si2O6. Let's say. But I can tell you, this orthopyroxene may contain sodium, can contain calcium, can contain aluminium, can contain ferric iron, can contain titanium, may contain aluminium, it can contain a lot of things. But let's make it simple. Let's make it simple. It contains MgFe whole twice Si2O6. This is A is a phase and B is also another phase. Right? Here, quartz is always taken as a pure phase. It's not that it is pure, it's not 100% quartz. If you analyze any grain of any mineral of quartz with the best electron microprobe that you have, composition of SiO2 will not be 100%. Could be 98.4, 98.5, 97.5. There are other components as well, but in small amounts. So, for all practical purposes, we consider quartz as a pure phase. When I say pure phase, click, click, activity 1. Have you understood? Back to thermodynamics, activity 1. But orthopyroxene has this formula. So what happens, this can be divided into two parts, Mg2Si2O6 and Fe2Si2O6. This is enstatite and this is ferrocyanide. Now, the composition of this orthorhombic pyroxene will vary between enstatite and ferrocyanide. Magnesium end member, iron end member. Have you understood? Magnesium end member and iron end member. These are called phase component. These are called phase components. The two end members the end member composition that describe the chemical variability of a mineral are called its phase components. Have you understood? The end member component that describes the chemical variability of the composition of a phase are called phase components. Does quartz have a phase component? Yes, it does. Yes, it does. Who said it doesn't contain phase components? But its phase component is SiO2. It's a single phase component of a phase. That is what is called a pure phase, where the phase is composed of one phase component. That's a pure phase. And when you have a situation like this, more than one phase component, this mineral is called a solid solution phase. Solid solution, see. So you can conceive of XMG in OPX is equal to Mg divided by Mg plus Fe. And XFE OPX is equal to Fe divided by Mg plus Fe. Or in other words, XMG OPX plus XFE OPX is equal to 1.0. For quartz, XSiO2 in quartz is equal to 1 always. So here there can be a variation. Here, no variation. Okay? So we have talked a little bit now about phase and phase components. Okay? I think in the next class we will elaborate on this. Right? Thank you.